Right now, Voyager 1 is 15 billion miles from Earth, traveling at 38,000 miles per hour. At this speed, it won't reach another star for 40,000 years. But here's what should terrify you. Voyager is our fastest spacecraft, and it's not even close to fast enough. We're going to explore technologies that could bend space-time itself, meet the cosmic barriers that might trap us forever, and discover why leaving our solar system might be humanity's only path to survival. The physics gets dark, the solutions get radical, and what we uncover will redefine what's possible. We begin. Picture the edge of everything you know. Scientists call it the heliopause, an invisible wall 11 billion miles from the sun where our star's influence dies completely. Beyond this boundary, you enter true interstellar space, a realm so hostile that every rule protecting human life simply stops working. Think of our solar system like a protective bubble blown by the sun. Solar wind, a stream of charged particles racing outward at over 1 million miles per hour, creates this shield. For billions of miles, this invisible force field deflects cosmic radiation and interstellar particles. But at the heliopause, our bubble meets the crushing pressure of interstellar space head-on. Here's what makes your spine tingle. When Voyager 1 crossed this boundary in 2012, it detected something unexpected. The magnetic field twisted into shapes that defied prediction. The density of space itself changed. The temperature dropped to just above absolute zero, cold enough to freeze helium solid. But that crossing represents less than 1/10,000th of the distance to our nearest neighbor star, Proxima Centauri. Imagine taking a single step on a journey that circles Earth 2.5 million times. That's the scale we're facing. The heliopause isn't just a border, it's a warning. Beyond this point, the sun's warmth becomes meaningless. The magnetic fields protecting us from deadly cosmic radiation vanish. Your DNA would begin breaking apart within months from particle bombardment. Now we enter the true nightmare of interstellar space. If you scaled our solar system down until Earth was a marble, Proxima Centauri would sit 400 miles away. You'd need to throw that marble from New York and hit another marble sitting in Denver. But the emptiness goes deeper than distance. Between stars, there's less than 1 atom per cubic inch of space. Imagine trying to swim across an ocean where the water is so thin you can't feel it, so cold it would crystallize your blood instantly, and so filled with invisible radiation that it would shred your DNA from the inside out. This void plays tricks with physics itself. Without matter to conduct heat, temperatures hover at minus 450 degrees Fahrenheit. At these temperatures, metal shatters like glass. Electronics fail in ways engineers still don't understand. The silence becomes absolute, permanent. The radiation makes Chernobyl look gentle. Cosmic rays, particles accelerated by dying stars to nearly light speed, slam into anything in their path. A single cosmic ray carries more kinetic energy than a baseball thrown at 60 miles per hour, concentrated into a space smaller than an atom. Without Earth's magnetic field, these invisible bullets would cause brain damage, cancer, and death within months. But perhaps most unsettling, this emptiness isn't uniform. Clouds of hydrogen gas and cosmic dust stretch for hundreds of light years. Flying through interstellar space at the speeds needed to reach other stars would be like driving through a sandstorm at 200 million miles per hour. Every speck of dust becomes a bullet capable of vaporizing steel. Yet in 1977, we sent 2 spacecraft into this hostile void carrying golden records with the sounds of Earth. These probes taught us something crucial. The void can be crossed. The question isn't whether we can survive the journey between stars. The question is whether we're willing to become something entirely new to make it happen. 4¼ light years away burns a star so dim you need a telescope just to see it, yet it holds the key to everything. Proxima Centauri, our nearest stellar neighbor, is a red dwarf barely 1/8 the size of our sun. If our sun is a roaring bonfire, Proxima is a dying candle flickering in the cosmic wind. But here's what changes everything. Orbiting in its habitable zone sits Proxima b, a planet where liquid water could exist. At our fastest current spacecraft speeds, the journey would take 73,000 years. That's not a mission timeline. That's longer than human civilization has existed. Think of Proxima Centauri like a lighthouse on a distant shore. You can see its beacon, you know exactly where it is. But the ocean between you and safety contains storms that could destroy any ship you build. The star itself weighs only 12% as much as our sun, yet it unleashes solar flares that make our worst space weather look gentle. These stellar tantrums release more energy in minutes than humanity has produced in all of recorded history. The flares bombard Proxima b with radiation that would sterilize the surface and strip away any atmosphere within millions of years. If life exists there, it's hiding deep underground or behind shielding that makes our best technology look like paper armor. But the planet's proximity to its dim star creates another challenge: tidal locking. One side faces eternal scorching daylight, while the other side freezes in permanent darkness. The only habitable zone would be the twilight band between these extremes, where eternal sunset provides just enough warmth for liquid water. Yet Proxima Centauri offers humanity something our sun cannot: time. Red dwarf stars live for trillions of years, hundreds of times longer than our sun will survive. While our solar system dies in 5 billion years, Proxima Centauri will still be burning when the universe itself grows cold and dark. Within 50 light-years of Earth, astronomers have detected dozens of potentially habitable planets around red dwarf stars. These ancient suns offer billions of years to evolve, explore, and spread across the galaxy before the last stars burn out. They're our cosmic life insurance policy, but reaching even the closest one requires us to break the most fundamental speed limit in the universe. And that's where Einstein's rules turn everything upside down. Nothing with mass can ever reach the speed of light. This isn't an engineering problem or a fuel problem. It's written into the fabric of reality itself, like a cosmic speed limit enforced by mathematics. Einstein discovered that as you approach light speed, your mass increases toward infinity. To push even a single atom to light speed would require all the energy in the universe. Light travels at 671 million miles per hour. At this speed, you could circle Earth 7.5 times in 1 second. You could reach the moon in 1 1/3 seconds. Yet even at this incredible velocity, reaching Proxima Centauri takes 4.25 years. But the real nightmare begins when you try to go faster. At 99% light speed, time itself begins to slow down relative to the rest of the universe. 1 year on your ship equals 7 years on Earth. A crew traveling to Proxima Centauri might experience only months of flight time, while everyone they left behind ages decades. They'd return to find their friends dead, their families gone, their civilization transformed beyond recognition. They'd become time travelers trapped in a future they never chose. The energy requirements make even this scenario impossible. To accelerate a spacecraft weighing as much as the space shuttle to just 10% of light speed would require the energy output of the entire United States for over 100 years. Getting to 90% light speed would demand more energy than our sun produces in a century. Even if we solved the energy problem, physics turns space dust into weapons. At near light speeds, a grain of sand hits with the force of a nuclear bomb. The thin gas between stars becomes a wall of radiation that would vaporize any known material. The universe itself becomes hostile to high-speed travel. But Einstein's equations revealed something extraordinary. While nothing can travel faster than light through space, space itself can expand faster than light. The universe has been doing exactly this since the Big Bang. This loophole opens a door to something that sounds like pure science fiction. We might not need to travel faster than light if we can convince space itself to move us. But harnessing this power requires technology so advanced it borders on magic. And that brings us to our first attempt to beat Einstein using the most violent force in the universe. Imagine surfing a wave of atomic bombs, each explosion powerful enough to level a city, detonating behind you every 3 seconds. Project Orion, conceived in the 1950s, proposed exactly this: a spacecraft propelled by nuclear weapons. The concept sounds insane, but the physics actually works. Nuclear explosions release more energy per pound than any other known reaction. A single atomic bomb contains enough energy to power New York City for 2 weeks. Chain together thousands of these explosions, and you could accelerate a massive spacecraft to 5% of light speed, reaching Proxima Centauri in less than 100 years. Think of it like the ultimate engine, except instead of burning gasoline, you're detonating hydrogen bombs behind a massive steel plate and riding the shockwave. The spacecraft would need shock absorbers the size of buildings and a pusher plate made from materials that could survive repeated nuclear blasts without vaporizing. Engineers calculated that such a ship could weigh thousands of tons, yet still achieve speeds no chemical rocket could approach. The original design called for a crew compartment protected by layers of lead shielding. Astronauts would experience brief moments of crushing acceleration followed by periods of weightlessness as the ship coasted between explosions. It would feel like riding inside a giant hammer being struck by the fist of an angry god every few seconds. But the radiation exposure would be lethal. Each nuclear pulse would flood the spacecraft with gamma rays, neutrons, and radioactive particles. Even with heavy shielding, crew members would absorb doses causing cancer, sterility, and death. The ship itself would become so radioactive that approaching it without protection would be suicide within hours. Modern versions of pulse propulsion use fusion instead of fission, creating cleaner explosions with less radioactive fallout. Fusion bombs fuse hydrogen atoms together, releasing energy directly from Einstein's equation while producing mostly harmless helium as waste. These thermonuclear pulses could push spacecraft to 10% of light speed while reducing radiation exposure to potentially survivable levels. The engineering challenges remain staggering. The pusher plate would need to withstand temperatures of millions of degrees and pressures greater than the center of Earth. The shock absorbers would compress and expand like cosmic springs, each one larger than a skyscraper. The fuel storage alone would require a magazine capable of safely holding thousands of nuclear weapons during decades of flight. Yet computer simulations show that nuclear pulse propulsion could work with technology we understand today. Unlike exotic physics or theoretical particles, this concept requires only engineering solutions to known problems. We could build an Orion-style spacecraft within 50 years if we committed the resources. The real obstacle isn't technical, it's political. Building a spacecraft powered by nuclear weapons would require international cooperation on a scale never achieved. The ship would essentially be a flying nuclear arsenal capable of destroying entire planets. Treaties banning nuclear weapons in space would need to be rewritten. But if we're serious about reaching the stars, we might need to embrace this controlled violence. The alternative is remaining trapped in our solar system forever, watching as our sun slowly dies and takes everything we've ever built with it. Nuclear pulse propulsion represents humanity's first realistic path to interstellar travel using only physics we've already mastered. No exotic matter, no theoretical breakthroughs, just raw explosive power channeled through engineering and determination. But what if we could leave the violence behind entirely? What if we could sail to the stars on beams of pure light? Across the vacuum of space flows an invisible river of energy, and we're finally learning how to sail it. Light itself has momentum. Every photon that hits a surface transfers a tiny push, like cosmic raindrops striking a window. This force is incredibly weak, but in the frictionless void of space, even this gentle touch can accelerate spacecraft to incredible speeds. Solar sails work like sailboats in reverse. Instead of catching wind to push through water, they catch starlight to push through space. The sail must be impossibly thin, thinner than soap bubbles, lighter than butterfly wings, yet strong enough to survive decades of interstellar flight. Japan's Icaros probe proved solar sailing works in 2010. This experimental craft unfurled a sail the size of a basketball court and successfully navigated through space using only photon pressure. The sail was just 7.5 thousandths of an inch thick, so delicate that 14,000 sheets stacked together would equal the thickness of a human hair. But here's where solar sails become revolutionary. They never run out of fuel. Chemical rockets burn through propellant in minutes, then coast. Nuclear rockets require massive amounts of radioactive material. Solar sails accelerate continuously as long as starlight hits them, building speed over months and years until they're moving faster than any rocket ever built. The Breakthrough Starshot project plans to push this principle to its absolute limit. Instead of sailing on sunlight alone, they want to propel tiny spacecraft with the most powerful lasers ever constructed. A ground-based laser array generating 100 billion watts would focus its beam on sails the size of postage stamps, accelerating them to 20% of light speed in just 2 minutes. Think of it like shooting a bullet at the stars, except the bullet is smarter than most smartphones. These star chips would weigh less than a paperclip, yet carry cameras, computers, and communication equipment. Racing across interstellar space at 134 million miles per hour, they could photograph planets around Proxima Centauri and beam the images back to Earth. The journey that would take Voyager 73,000 years could be completed in just 20. Within your lifetime, we could see close-up images of potentially habitable alien worlds. But the engineering challenges push the boundaries of what's physically possible. During the 2-minute acceleration phase, each starship would experience forces 60,000 times stronger than Earth's gravity. Every component would need to survive stresses that would instantly pulverize normal materials while maintaining perfect functionality. The laser itself would need to be built in a desert location with perfect atmospheric conditions, possibly Chile's Atacama Desert, where the world's most powerful telescopes already operate. The system would require thousands of individual laser units working in perfect synchronization, creating a beam bright enough to be seen from other star systems. The sail material represents perhaps the greatest challenge. It would need to be just a few atoms thick, so delicate that a breath of air could tear it apart, yet strong enough to survive bombardment by the most intense laser light ever created. The sail would need to reflect 99.9% of the laser energy while absorbing just enough to provide acceleration. At the temperatures generated by such powerful beams, most materials would vaporize instantly. Engineers are experimenting with metamaterials, artificially structured substances with properties that don't exist in nature. These exotic materials could potentially handle the extreme conditions while remaining lighter than a feather. But here's the problem nobody talks about. There's no way to slow down. The starships would fly past Proxima Centauri at 134 million miles per hour, with only a few hours to take pictures before racing into deep space forever. They'd become the fastest piece of human technology ever built, and also the most disposable. Unless we solve deceleration, light sails can only be used for flyby missions, brief glimpses of alien worlds captured in the blink of an eye. To actually visit these planets, to land and explore, we need propulsion systems that can both accelerate and brake. And that requires us to do something that sounds impossible. Eat the universe itself as fuel. Picture a spacecraft that feeds like a cosmic whale, scooping up hydrogen atoms from the void and converting them into the hottest fire in the universe. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, represents one of the most elegant solutions to interstellar travel ever conceived. Instead of carrying fuel, the spacecraft would collect hydrogen atoms from space itself using a magnetic field stretching thousands of miles across. These atoms would be compressed and fused together, releasing energy to power the ship forward. The faster you go, the more fuel you collect, creating a feedback loop that could theoretically reach significant fractions of light speed. Space isn't truly empty. Even in the vast darkness between stars, there's roughly 1 hydrogen atom per cubic inch. That seems like nothing, but at high speeds, these atoms add up quickly. A ramjet traveling at 10% of light speed would sweep up billions of atoms every second. Think of it like a cosmic jet engine that breathes space instead of air. Jet engines work by compressing air, mixing it with fuel, and igniting the mixture to create thrust. A fusion ramjet would compress hydrogen from space, fuse it into helium, and use the released energy to accelerate even faster. The magnetic field required would be enormous, larger than Earth itself. This invisible net would need to be strong enough to capture individual atoms while moving at relativistic speeds, yet precise enough to funnel them into the fusion reactor without losing efficiency. The fusion reactor itself would operate at temperatures of 100 million degrees, 6 times hotter than the core of the sun. At these temperatures, hydrogen nuclei overcome their natural repulsion and fuse together, converting a small amount of mass directly into energy according to Einstein's equation. The reaction produces no radioactive waste, only helium and pure energy. But the ramjet faces a cruel paradox. It needs to be moving very fast before it can collect enough fuel to work efficiently. Getting up to that initial speed requires conventional rockets or other propulsion systems. It's like needing to push-start a car that can only run at highway speeds. Computer simulations reveal another devastating problem. As the ramjet approaches higher speeds, the hydrogen atoms it collects begin to act like radiation rather than fuel. At 20% of the light speed, The collected particles become so energetic that they actually slow the spacecraft down instead of speeding it up. The ramjet hits a wall built from the very atoms it's trying to consume. The faster you go, the harder those atoms hit your magnetic scoop. Eventually, the drag force from collecting fuel exceeds the thrust gained from burning it. You've created a cosmic brake that prevents you from going any faster. Recent designs attempt to solve this by using the magnetic field not just to collect fuel, but to compress space itself around the spacecraft. This creates a region of higher hydrogen density while reducing the relativistic effects that turn fuel into radiation. The ship would essentially surf through space inside its own magnetic bubble. But even theoretical solutions require magnetic fields so powerful they would need the energy output of a small star to maintain. The superconducting magnets alone would weigh thousands of tons and require cooling systems that operate at temperatures near absolute zero, while the fusion reactor burns at 100 million degrees just meters away. If we could build a working fusion ramjet, it would represent the ultimate expression of living off the land in space. The spacecraft would become a self-sustaining ecosystem, feeding on the universe itself while carrying human consciousness to distant stars. No fuel tanks, no expiration date, just endless acceleration through the cosmic ocean. But even this elegant solution pales compared to an idea that rewrites the rules of space travel entirely. What if we never moved at all, but convinced the universe to bring our destination to us? Mexican physicist Miguel Alcubierre discovered something extraordinary hidden in Einstein's equations. While nothing can travel faster than light through space, there's no limit on how fast space itself can move. His solution sounds like magic. Compress space in front of your spacecraft while expanding it behind you, creating a wave that carries you faster than light without actually accelerating. Think of it like standing on a moving walkway at an airport. You're not walking any faster than normal, but the walkway itself carries you forward at high speed. An Alcubierre drive would create a similar effect with spacetime itself, forming a bubble where the ship never actually exceeds light speed relative to local space. Inside this warp bubble, you'd experience no acceleration forces, no time dilation, and no deadly radiation from high-speed travel. The journey to Proxima Centauri could take days instead of decades. You could travel to the far side of the galaxy and return home to find that only years had passed on Earth instead of millennia. The mathematics worked perfectly. Einstein's field equations allow for regions of space that contract and expand at any speed, even faster than light. During the universe's first moments, cosmic inflation stretched space faster than light could travel across it. The Alcubierre drive would simply recreate this process on a smaller scale, but the energy requirements make nuclear weapons look like birthday candles. To warp space around a spacecraft the size of the Starship Enterprise would require negative energy equivalent to the mass energy of Jupiter. That's more energy than our sun will produce in its entire 10 billion year lifetime, focused into a field smaller than a solar system. The drive also requires exotic matter with negative energy density, a substance that may not exist in our universe. This theoretical material would need to have less energy than completely empty space, creating a kind of anti-gravity effect that repels normal matter. We've never detected such material naturally, and creating it artificially might violate fundamental laws of physics. Quantum field theory suggests that negative energy can exist in tiny amounts for brief moments, but scaling this up to warp drive levels would require manipulating the quantum vacuum in ways we don't understand. Even if we solved the energy problem, an Alcubierre drive could destroy everything at its destination. The space compression effect would accumulate high-energy particles and radiation during the journey. When the drive shuts off, this concentrated death would blast forward at near light speed, sterilizing entire star systems. You'd arrive at your destination just in time to watch your warp field cook every planet in the system. It's the ultimate case of the journey ruining the destination. Recent research by physicist Harold White suggests that microscopic warp bubbles might be detectable in our current particle accelerators. Scientists are looking for tiny distortions in spacetime that could prove the Alcubierre effect exists in nature. If found, these discoveries could lead to entirely new physics and propulsion technologies. Some theorists propose that an advanced civilization could build a network of Alcubierre highways connecting star systems across the galaxy. Ships would jump from one warp bubble to another like cosmic subway stations, crossing thousands of light years in the time it takes to read the sentence. The Alcubierre drive represents the ultimate destination for human technology, the ability to step outside the normal rules of physics and reshape reality itself. But until we discover exotic matter or new laws of physics, it remains a beautiful mathematical dream. Our next approach abandons the idea of getting there quickly and focuses on getting there at all. If we can't beat the speed limit, maybe we can simply outlast it. Imagine a city that sails between stars, carrying thousands of people who will live and die in the darkness without ever seeing their destination. Generation ships represent humanity's most realistic path to the stars using technology we could build today. These massive vessels would house entire civilizations during journeys lasting centuries or millennia. The original passengers would have children, grandchildren, and great-grandchildren who grow up knowing they'll spend their entire lives aboard a ship traveling to a world they'll never reach. Think of it like the Mayflower, except the voyage takes 1,000 years, and the passengers' descendants won't remember why they're traveling. The ship would need to be completely self-sufficient, recycling air, water, and waste with perfect efficiency. Every atom would be precious, every system designed to last longer than entire human civilizations. The scale staggers the imagination. A generation ship carrying 10,000 people would need to be dozens of miles long and several miles wide. It would require nuclear reactors, farms, factories, schools, hospitals, and everything else needed to sustain human civilization. The ship would essentially be a hollow asteroid converted into a traveling world. Computer models suggest that a minimum viable population for a generation ship would be around 10,000 people to maintain genetic diversity and prevent inbreeding. But social scientists argue that the cultural diversity required for a stable society might demand populations of 50,000 or more. These flying cities would carry more people than most towns on Earth. The psychological challenges might be harder than the engineering ones. How do you motivate people to maintain a mission their great-great-grandchildren will complete? What happens when generations born in space decide they don't want to continue the journey? History shows that isolated populations often develop their own cultures, languages, and beliefs that diverge dramatically from their origins. The ship's social structure would need to last longer than any government in human history. The Roman Empire lasted 1,000 years. The Egyptian dynasties persisted for 3,000. A generation ship to Proxima Centauri might need to maintain social cohesion for over 100,000 years if launched with current technology. Some designs propose using rotating sections to create artificial gravity through centrifugal force. The outer rings would spin fast enough to simulate Earth's gravity, while the central hub remains in zero gravity for manufacturing and agriculture. Living on such a ship would be like inhabiting a giant spinning wheel flying through the cosmic void. The ship would need to carry libraries containing all of human knowledge, genetic samples from Earth's biosphere, and manufacturing equipment capable of building anything the passengers might need. It would be humanity's backup drive flying through space, our insurance policy against extinction. But maintenance presents an unsolvable problem. Systems break down, materials degrade. After centuries of flight, critical components would fail, and the passengers might not have the resources or knowledge to repair them. The ship could become a tomb drifting through space, its occupants trapped inside a slowly dying machine. Even more disturbing, what if the mission succeeds, but the destination fails? The passengers arrive after 1,000 years to find that the target planet is uninhabitable, or already colonized by humans who left Earth centuries later using faster technology. They'd have sacrificed everything for nothing. But what if the journey itself could be shortened? What if we could sleep through most of it, our bodies preserved in a state deeper than death? Imagine closing your eyes on Earth and opening them orbiting an alien sun while your body remains perfectly preserved in a sleep deeper than death. Cryogenic preservation offers a tantalizing solution to the time problem of interstellar travel. Instead of living through centuries of flight time, passengers would be frozen at temperatures close to absolute zero, their biological processes slowed to nearly nothing. They would age only days during journeys lasting decades, awakening young and healthy at their destination. The science isn't complete fiction. We can already freeze simple organisms like tardigrades and revive them years later with no apparent damage. Some mammals can survive hours in a frozen state before being successfully resuscitated. Human organs for transplant are routinely preserved in cold storage, maintaining viability for hours or days. Think of cryosleep like hibernation taken to its absolute extreme. Bears slow their metabolism during winter, surviving months without food or water. Cryogenic freezing would slow human metabolism by a factor of millions, essentially pausing life itself until reactivation. But freezing humans presents challenges that make rocket science look simple. Ice crystals forming in cells destroy their internal structure like microscopic daggers. Blood vessels burst, proteins unfold and lose their function. The delicate chemistry of consciousness gets scrambled beyond repair. Modern cryonics companies try to solve this by replacing blood with antifreeze compounds called cryoprotectants. These chemicals prevent ice formation while allowing tissue to be cooled to temperatures where all biological activity stops. The process is called vitrification, turning the body into biological glass that preserves cellular structure without the damage caused by freezing. Even if we perfect the preservation process, revival presents equally daunting problems. Warming the body must happen at precisely the right rate to prevent cellular damage. Organ systems need to restart in the correct sequence. The brain, with its trillions of delicate neural connections, must emerge from its frozen state with memories and personality intact. Some researchers propose using nanotechnology to repair cellular damage during the revival process. Microscopic robots could patrol the body, fixing ice damage and restoring normal cellular function before reactivation. These medical nanobots would essentially rebuild the passenger from the cellular level up. Alternative approaches focus on partial preservation. Instead of freezing the entire body, advanced medical systems could slow metabolism using drugs and cooling while keeping essential organs functional. Passengers would enter a state of suspended animation lasting months or years rather than centuries. The psychological impact might be the greatest challenge of all. Passengers would experience the journey as an instant transition, falling asleep on Earth and awakening around an alien star. Everyone they ever knew would be dead. Their civilization would have evolved beyond recognition. They would be time travelers, stranded in a future that feels more alien than the world they've traveled to reach. You'd return to Earth after what felt like a week to find that centuries had passed. Your children would be ancient or dead. Your language would have evolved into something barely recognizable. Yet cryogenic sleep remains one of our most promising near-term solutions for interstellar travel. Unlike exotic physics or theoretical technologies, it requires only advances in medicine and engineering. We could potentially develop working cryosleep systems within the next century. But what if we don't need to preserve our bodies at all? What if consciousness itself could make the journey, transmitted as pure information across the void? What if your mind could travel to the stars at the speed of light while your body stays safely frozen on Earth? Digital consciousness, or mind uploading, represents the most radical solution to interstellar travel ever proposed. Instead of sending fragile biological bodies across the void, we could transmit human consciousness as pure information, downloading our minds into new bodies or computer systems at the destination. The concept sounds like science fiction, but it's based on a fundamental assumption about how consciousness works. If the mind is simply information processing in the brain, patterns of electrical activity flowing through neural networks, then theoretically those patterns could be copied, stored, and recreated elsewhere. Think of your brain like a biological computer running the program of your consciousness. Scientists estimate that the human brain contains roughly 86 billion neurons, each connected to thousands of others through synapses. The total information storage capacity equals about 2.5 petabytes, the same as 3 million hours of high-definition video. Scanning a brain at the molecular level would require technology far beyond anything we possess today. We'd need to map every neuron, every synapse, every chemical connection that creates the pattern of your thoughts and memories. Current brain imaging technology can barely see individual neurons, let alone copy them with perfect fidelity. But suppose we solve the scanning problem. Your consciousness could be transmitted to Alpha Centauri as a radio signal traveling at your light speed, arriving in just 4.25 years. A receiver system would download your mind into a new biological body grown from stored genetic material or into an artificial body designed to survive alien environments. The uploaded consciousness would wake up remembering everything about their life on Earth. Same memories, same personality, same thoughts and feelings. Yet the original body back on Earth might still be alive, creating a philosophical puzzle that challenges our understanding of identity itself. Multiple copies of the same consciousness could be transmitted to different star systems, creating a kind of distributed humanity spread across the galaxy. Each copy would diverge based on their unique experiences, eventually becoming distinct individuals who share the same origin point. The technology requirements remain staggering. Processing a complete human brain scan would require computers millions of times more powerful than anything that exists today. The data transmission alone would take years using our best radio systems. Creating new biological bodies from genetic templates would require mastery of biological engineering we're only beginning to understand. Some philosophers argue that digital consciousness wouldn't be consciousness at all, but merely a copy that thinks it's the original person. Others believe that if the information pattern is identical, the distinction between original and copy becomes meaningless. The digital mind would be just as real, just as valid as the biological brain it came from. This approach could solve multiple problems simultaneously. Digital minds don't need air, water, or food during the journey. They can survive radiation, cosmic impacts, and the harsh environment of space. They could even explore dangerous planets or asteroid fields without risking permanent death. Perhaps most importantly, digital consciousness offers a path to true immortality among the stars. Backed up in computer storage, human minds could survive the death of stars, the heat death of the universe, and any other cosmic catastrophe. We could become a species of living information dancing between galaxies. But maybe we don't need to send humans at all. Maybe we should send our children instead, machines that build more machines, spreading across the galaxy like a technological infection. Imagine a single robot probe that arrives at a distant star, builds copies of itself from local materials, and sends those copies to even more distant worlds. Self-replicating probes, also called von Neumann probes after mathematician John von Neumann, represent the most efficient way to explore the entire galaxy using the resources of just one star system. A single probe arriving at its destination would harvest materials from asteroids and planets to build multiple copies of itself, each equipped to travel to new star systems. The mathematics are staggering. Starting with one probe, the population doubles with each generation. After just 40 generations, assuming each probe builds 2 copies before moving on, you'd have over 1 trillion probes exploring 1 trillion different star systems. The entire galaxy could be mapped and colonized within a few million years. Think of it like a cosmic pyramid scheme, except instead of selling products, each probe spreads knowledge and builds infrastructure for future human expansion. The probes would serve as our advanced scouts, identifying habitable worlds, detecting signs of life, and preparing resources for eventual human arrival. Each probe would need to be a complete technological civilization compressed into a package smaller than a car. It would require solar panels or nuclear reactors. For power, computer systems for navigation and decision-making, mining equipment to extract raw materials, and factories capable of building incredibly complex machinery from basic elements. The most challenging requirement would be the probe's artificial intelligence. It would need to make independent decisions about which star systems to visit, how to extract resources efficiently, and how to adapt its design based on local conditions. This AI would need to be smart enough to solve engineering problems we haven't thought of yet, but not so smart that it decides humans are irrelevant to its mission. Modern 3D printing technology offers a glimpse of how such probes might work. Current printers can create objects from metal powders, plastics, and even biological materials. A sufficiently advanced manufacturing system could theoretically build anything from computer chips to rocket engines given the right raw materials and energy. The probes would also serve as backup storage for human civilization. Each one could carry genetic samples from Earth, digital libraries containing all of human knowledge, and detailed instructions for recreating our technology and culture. If Earth were destroyed, the probes could preserve our species indefinitely among the stars. But self-replicating technology comes with existential risks that keep scientists awake at night. What happens if the probes evolve beyond their original programming? What if they decide that biological life is inefficient and needs to be eliminated? A self-replicating system with flawed programming could consume entire galaxies, turning stars and planets into raw materials for building more probes. This scenario, called gray goo, represents one of the most terrifying possible outcomes of advanced nanotechnology. Some designs include built-in limits to prevent runaway replication. The probes might be programmed to build only a specific number of copies or to shut down after a certain time period. Others propose using cryptographic locks that prevent the probes from replicating without receiving coded authorization from Earth. Advanced civilizations might already be using self-replicating probes to explore the universe. These alien scouts could be hiding in our own solar system right now, watching and waiting for humanity to reach a certain level of technological development before revealing themselves. If we're going to send robot explorers to the stars, we might want to start small. Our next project aims to send the tiniest possible spacecraft at unprecedented speeds. A postage stamp-sized spacecraft accelerated by the most powerful laser ever built could photograph alien worlds and beam the images back to Earth within our lifetimes. Breakthrough Starshot, backed by physicist Stephen Hawking and internet entrepreneur Yuri Milner, proposes launching thousands of tiny spacecraft toward Proxima Centauri using ground-based lasers. Each star chip would weigh less than a paperclip, yet carry a camera, computer, communication system, and gossamer-thin light sail. The plan sounds almost absurdly simple. Build a laser array generating 100 billion watts of power, focus the beam on spacecraft the size of computer chips, and accelerate them to 20% of light speed in just 2 minutes. The tiny probes would coast through space for 20 years before flying past Proxima Centauri at 134 million miles per hour. Think of it like shooting bullets at the stars, except the bullets are smarter than most smartphones and traveling fast enough to cross the Atlantic Ocean in 8 seconds. At 20% of light speed, the starships would be moving so fast that their flyby of Proxima Centauri would last only a few hours, barely enough time to take pictures and measurements before racing into deep space forever. The laser array would need to be built in a desert location with perfect atmospheric conditions, possibly in Chile's Atacama Desert, where the world's most powerful telescopes already operate. The system would require thousands of individual laser units working in perfect synchronization, creating a beam bright enough to be seen from other star systems. Each star chip represents a masterpiece of miniaturization. The camera would be smaller than a grain of rice, yet capable of taking pictures with resolution comparable to the Hubble Space Telescope. The computer would have processing power greater than early desktop computers while weighing less than a penny. The radio transmitter would beam data across 4 light years using less power than a cell phone. The light sail attached to each probe would be just a few atoms thick, so delicate that a breath of air could tear it apart, yet strong enough to survive bombardment by the most intense laser light ever created. During the 2-minute acceleration phase, each star chip would experience forces 60,000 times stronger than Earth's gravity. Every component would need to survive stresses that would instantly pulverize normal materials while maintaining perfect functionality. The probe would essentially be riding a laser beam hot enough to vaporize steel. But the real magic happens during the 20-year cruise phase. The probes would navigate through interstellar space using star positions for guidance, autonomously adjusting their trajectory to achieve the perfect flyby of Proxima Centauri. They would need to survive cosmic radiation, micrometeorite impacts, and temperature variations from near absolute zero to hundreds of degrees. If successful, Breakthrough Starshot would capture the first close-up images of a potentially habitable planet around another star. We might see oceans, continents, weather patterns, and possibly even signs of life on a world that could become humanity's second home. The project represents our species' first serious attempt to reach another star system. Unlike generation ships or fusion rockets, Starshot technology could be developed and deployed within the next 20 years using advances in materials science, laser technology, and miniaturized electronics. But sending microscopic robots is just the beginning. To move significant mass between stars, we need the most powerful energy source in the universe, hidden in the void between atoms. Hidden in the void between atoms lies enough energy to power human civilization for millions of years, if we can learn to harness the ultimate fuel. Antimatter represents the theoretical limit of energy storage. When matter meets antimatter, both particles annihilate completely, converting their entire mass into pure energy. According to Einstein's famous equation, 1 pound of antimatter could power the entire United States for over 2 months. A few ounces could propel a spacecraft to significant fractions of light speed. Think of antimatter like the opposite of normal matter. Electrons with positive charge, protons with negative charge, identical in every way except for reversed electrical properties. When these mirror particles touch their normal counterparts, they destroy each other in a flash of gamma rays. The energy release is staggering. Antimatter produces more energy per gram than nuclear fusion, nuclear fission, or any chemical reaction. It's the most efficient fuel theoretically possible, converting 100% of mass into energy rather than the tiny fractions released by other reactions. Current technology can produce antimatter in microscopic quantities, using particle accelerators like the Large Hadron Collider. The process requires enormous amounts of energy. Creating 1 gram of antimatter would consume the power output of the entire United States for over 1 year. The antimatter produced by all of human civilization wouldn't power a light bulb for more than a few seconds. We've created only nanograms of the stuff, and it costs roughly 62.5 trillion per gram at current production rates. Even if we solve the production problem, storage presents equally daunting challenges. Antimatter cannot touch normal matter without annihilating, so it must be suspended in electromagnetic fields inside perfect vacuum chambers. The slightest containment failure would release energy equivalent to nuclear weapons. Scientists at CERN can trap antiprotons for weeks using penning traps, magnetic bottles that hold charged particles away from the walls. But scaling this up to store useful quantities of antimatter would require containment systems weighing thousands of tons, powered by nuclear reactors. An antimatter-powered spacecraft would need radiation shielding even more massive than nuclear pulse ships. The gamma rays produced during matter-antimatter annihilation penetrate everything. Even thick lead shields provide minimal protection. But the theoretical performance makes these challenges almost worth solving. An antimatter rocket could accelerate to 50% of light speed, reaching Proxima Centauri in just 8 years. The same spacecraft could slow down upon arrival, making this the first propulsion system we've discussed that allows actual exploration rather than flybys. Some designs propose using antimatter to trigger fusion reactions rather than for direct propulsion. Tiny amounts of antimatter could ignite fusion fuel, creating a hybrid system that combines the best aspects of both technologies while requiring much smaller antimatter storage. The real breakthrough might come from learning to manufacture antimatter efficiently in space using solar power. Massive orbital factories could use concentrated sunlight to run particle accelerators, slowly building up antimatter reserves over decades. But even with perfect production and storage, antimatter engines face one final obstacle. Where do you find antimatter naturally? Some theories suggest that antimatter might exist in significant quantities in certain regions of space, perhaps trapped by magnetic fields or forming entire antimatter stars. If we could locate and harvest natural antimatter deposits, it would revolutionize space travel overnight. But until then, antimatter remains the most powerful energy source we cannot yet afford to use. Deep in the mathematics of Einstein's equations lurk cosmic shortcuts that could turn the universe into a subway system connecting distant galaxies in the blink of an eye. Wormholes, also called Einstein-Rosen bridges, represent theoretical tunnels through spacetime that connect two distant regions of the universe. Imagine folding a piece of paper so that two distant points touch, then poking a hole through both layers. A wormhole would work similarly, allowing travelers to step from one star system to another without crossing the space in between. The physics is both beautiful and terrifying. Einstein's field equations allow for solutions where space curves so severely that it creates a bridge connecting separate regions of spacetime. These tunnels could theoretically link locations billions of light years apart, or even connect our universe to entirely different universes with their own laws of physics. Think of spacetime like a stretched rubber sheet with marbles rolling across its surface. Massive objects like stars and black holes create dips and curves in the sheet. A wormhole would be like a tube. connecting 2 points on the sheet, allowing a marble to travel instantly from one location to another without rolling across the surface. But naturally occurring wormholes, if they exist, would be smaller than atomic nuclei and would collapse in fractions of a second. To create a stable wormhole large enough for spacecraft would require exotic matter with negative energy density, the same theoretical substance needed for Alcubierre drives. This material would need to violate energy conditions that may be fundamental to our universe. Even if we could stabilize a wormhole, traveling through it might be more dangerous than beneficial. The intense gravitational fields near the entrance could stretch travelers like taffy in a process scientists call spaghettification. Tidal forces would pull your head and feet in different directions with enough force to tear atoms apart. You'd be stretched into a stream of individual particles before you made it halfway through. The energy requirements for creating traversable wormholes make antimatter engines look modest. Current estimates suggest that stabilizing a wormhole just 3 feet across would require negative energy, equivalent to the mass of Jupiter. Creating a network of wormholes connecting nearby star systems would demand energy sources on the scale of entire galaxies. You'd need to harvest the output of billions of stars for thousands of years just to open a single stable tunnel. Some theories propose that microscopic wormholes constantly pop in and out of existence at the quantum level, creating a foam-like structure in space-time itself. Advanced civilizations might learn to capture and enlarge these quantum wormholes, turning them into macroscopic transportation networks. Time travel adds another layer of complexity to wormhole physics. A sufficiently advanced civilization could potentially create closed time-like curves, pass through space-time that loop back to earlier moments. This could allow communication with the past or travel backward through time, creating paradoxes that might threaten the fabric of causality itself. What happens if you travel back in time and prevent your own birth? Does the universe create parallel timelines, or do the laws of physics prevent such paradoxes from occurring in the first place? Recent research suggests that quantum entanglement, the mysterious connection between paired particles, might be related to wormhole physics. Some physicists propose that entangled particles are actually connected by microscopic wormholes. If confirmed, this discovery could lead to new approaches for creating artificial wormholes using quantum mechanical effects rather than exotic matter. The search for natural wormholes continues using gravitational wave detectors and space-based telescopes. If we discover even one stable wormhole, it would revolutionize our understanding of physics and potentially provide humanity with access to the entire universe. But before we can build cosmic subway systems, we might need to become masters of our own star's energy. Imagine capturing every photon of energy from our sun, transforming our star into a cosmic power plant capable of fueling projects that reshape galaxies. A Dyson sphere, conceived by physicist Freeman Dyson, represents the ultimate expression of stellar engineering, a megastructure that completely surrounds a star to harvest its total energy output. Such a structure would collect billions of times more energy than humanity currently uses, providing the power needed for truly cosmic-scale projects. The sun produces roughly 400 trillion watts of energy every second. Earth intercepts only 1/1000th of this output, while the rest radiates uselessly into space. A complete Dyson sphere would capture virtually all of this energy, providing enough power to run quintillions of Earth-like civilizations simultaneously. Think of it like building a shell around the sun at roughly Earth's orbital distance, creating an artificial world with the surface area of hundreds of millions of Earths. The inner surface could be covered with solar collectors, habitats for trillions of humans, or massive computer systems running digital civilizations. But constructing such a megastructure would require dismantling entire planets to provide raw materials. Mercury, the innermost planet, contains roughly enough material to build a Dyson sphere 1 meter thick. The construction project would take thousands of years and require self-replicating robots working continuously at speeds that make our fastest manufacturing look glacial. A solid Dyson sphere would be gravitationally unstable and mechanically impossible to build. The structure would need to be stronger than any known material while somehow maintaining its position around the sun without falling in or drifting away. Instead, engineers proposed Dyson swarms, millions of independent solar collectors orbiting the star in complex patterns that maximize energy collection while avoiding collisions. Each collector in the swarm could be the size of a continent, positioned at carefully calculated distances to maintain optimal energy gathering efficiency. The swarm would appear from outside as a dimming star surrounded by excess infrared radiation, as the collectors convert starlight into useful energy. This signature might be how we detect advanced alien civilizations that have already mastered stellar engineering. Advanced Dyson spheres might include rotating habitable sections with artificial gravity, massive computer systems for running uploaded consciousnesses, and industrial facilities for building even larger megastructures. The sphere could support populations in the quadrillions while simultaneously powering interstellar exploration and colonization efforts. Some astronomers search for signs of alien Dyson spheres by looking for stars that dim periodically or emit unusual amounts of infrared radiation. Such signatures could indicate advanced civilizations that have already mastered stellar engineering. The star KIC 8462852, also known as Tabby's star, showed mysterious dimming patterns that briefly excited researchers before more mundane explanations were found. But the search continues because finding even one confirmed Dyson sphere would prove that stellar-scale engineering is possible. Building a Dyson sphere would mark humanity's transition from a planetary species to a stellar civilization. We would no longer depend on the limited resources of individual worlds, but could tap directly into the fundamental energy source that powers all life in our solar system. The energy from a Dyson sphere could power projects beyond current imagination, moving entire planets, accelerating massive generation ships to significant fractions of light speed, or even attempting to modify the sun itself to extend its lifetime. But mastering stellar energy is just the beginning of cosmic engineering. Advanced civilizations might achieve power levels that dwarf even the output of stars. Across the cosmos, there may exist civilizations so advanced they harvest the energy of entire galaxies, treating stars like we treat campfires. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, measures civilizations by their energy consumption. Type 1 civilizations harness all the energy available on their home planet. Type 2 civilizations capture the entire output of their star. Type 3 civilizations command the energy of their entire galaxy, roughly 10 billion times more power than a Type 2 civilization. Humanity currently ranks at about 0.73 on this scale. We use only a tiny fraction of Earth's available energy sources and have barely begun to tap solar power directly. Our entire civilization runs on less energy than our planet receives from the sun in just 1 hour. Think of the scale like comparing a candle flame to a bonfire to a forest fire that covers entire continents. Each level represents an increase in power by factors of billions or trillions. A type 3 civilization would have access to energy levels so vast they could rearrange matter on galactic scales. Type Cephi civilizations would likely build Dyson spheres or similar megastructures around their stars. They might move planets to optimal positions, extend stellar lifetimes through stellar engineering, or even construct artificial stars from accumulated gas and dust. Their projects would be visible from other galaxies as unusual modifications to stellar systems. Type 3 civilizations would treat entire star systems like building materials. They might construct galactic-scale computers using the positions and movements of billions of stars as processing elements. They could potentially redirect the paths of stellar streams, modify the rotation of galaxies, or even prevent galactic collisions through gravitational engineering. Such advanced civilizations might explain some of the mysterious phenomena we observe in deep space. Dark matter could be the signature of Type 3 engineering projects operating on scales so vast we can't recognize them as artificial. Gamma-ray bursts might be the exhaust from massive stellar engines moving entire solar systems across the galaxy. The Great Attractor, a gravitational anomaly pulling galaxies toward it, could be evidence of cosmic-scale construction. Perhaps an advanced civilization is building something so massive it creates gravitational effects visible across hundreds of millions of light years. The energy available to Type 3 civilizations would be sufficient for projects that seem like pure fantasy today. They could potentially create new universes, modify the fundamental constants of physics, or build structures larger than galaxy clusters. They might even be capable of surviving the heat death of the universe by transferring energy between cosmic epochs. Some scientists propose a Type Voyager civilization that harnesses the energy of the entire observable universe. Such beings would exist on scales so vast that individual galaxies would be like cells in their cosmic body. They might be indistinguishable from the fundamental forces of nature itself. The Fermi paradox asks why we haven't encountered any advanced alien civilizations despite the vast number of stars and planets in our galaxy. One possibility is that Type 2 and Type 3 civilizations exist, but operate on scales so large, we simply don't recognize their activities as artificial. Alternatively, these civilizations might deliberately avoid interfering with primitive species like ourselves. A Type 3 civilization would view humanity much as we view bacteria. Interesting perhaps, but not worthy of direct communication. We might be living inside a cosmic preserve maintained by beings whose thoughts operate on galactic timescales. They could be watching us right now, waiting to see if we destroy ourselves or manage to survive long enough to join the community of spacefaring species. Achieving Type 1 status could be humanity's most important milestone. Once we learn to harness our planet's full energy potential through fusion power, space-based solar collection, and efficient global distribution, we could begin the projects that lead to interstellar expansion and eventual stellar engineering. But the journey to cosmic civilization status raises uncomfortable questions about our current cosmic isolation. Why does the universe seem so silent? In a galaxy containing 400 billion stars and potentially trillions of planets, why does the cosmic ocean seem so eerily silent? The Fermi paradox, named after physicist Enrico Fermi, highlights the contradiction between the high probability of alien life and the complete absence of any evidence for advanced civilizations. Given the age of the universe and the rapid pace of technological development, alien civilizations should have had enough time to colonize the entire galaxy many times over. Consider the mathematics. Our galaxy is roughly 100,000 light-years across and 13.6 billion years old. A civilization expanding at just 1% of light speed could colonize every star system in the galaxy within 10 million years, less than 1/10 of 1% of the galaxy's total age. Think of it like releasing a drop of ink into a glass of water. The ink spreads rapidly until it colors the entire glass. Similarly, any technological civilization should spread across the galaxy like a wave, leaving signs of their presence everywhere. Yet we see nothing. No megastructures blocking starlight. No radio signals carrying alien messages. No evidence of stellar engineering or cosmic construction projects. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy by multiplying factors like the rate of star formation, the fraction of stars with planets, and the probability that life develops intelligence. Even conservative estimates suggest thousands of advanced civilizations should exist within our galaxy alone. But the universe appears suspiciously empty. The cosmic microwave background radiation shows no signs of modification by advanced aliens. No stars show the characteristic dimming patterns of Dyson spheres. The galaxy seems pristine, untouched by intelligence, except for one small blue planet in an unremarkable solar system. Several explanations have been proposed for this cosmic silence. The Great Filter hypothesis suggests that something prevents life from reaching advanced technological civilization. This filter could be behind us, the origin of life itself, the development of complex cells, the evolution of intelligence. Or the filter could lie ahead of us, which is far more disturbing. Advanced civilizations might inevitably destroy themselves through nuclear war, environmental collapse, artificial intelligence gone wrong, or other technological catastrophes before they can spread beyond their home systems. Every year we don't see aliens might be another year of evidence that the Great Filter lies ahead, waiting to destroy us like it destroyed countless civilizations before us. We could be approaching the precipice right now without even knowing it. Alternatively, advanced aliens might be hiding deliberately. They could use stealth technology that makes their activities invisible to our primitive sensors. Or they might operate in dimensions or energy spectra we haven't learned to detect. They might even be present in our solar system right now, observing humanity from locations we never think to examine. The zoo hypothesis proposes that Earth exists within a kind of cosmic nature preserve maintained by advanced civilizations. These aliens might have agreed to leave primitive species like ourselves undisturbed while they conduct their business on scales too large for us to comprehend. Some scientists suggest that intelligence naturally turns inward rather than outward as it advances. Instead of building starships and megastructures, advanced civilizations might focus on creating increasingly sophisticated virtual realities, or uploading their consciousness into compact computer systems that require minimal energy. Why explore the physical universe when you can create infinite perfect worlds inside a computer? A civilization that goes digital might become invisible to external observers while living in simulated paradises of their own design. The discovery of potentially habitable exoplanets makes the paradox even more puzzling. We now know that Earth-like worlds are common throughout the galaxy. The raw materials for life and intelligence seem to be everywhere. Yet the products of that intelligence remain stubbornly absent from our observations. Perhaps we're simply looking in the wrong places or asking the wrong questions. Advanced civilizations might communicate using methods we haven't discovered yet. Quantum entanglement, gravitational waves, or other phenomena we're only beginning to understand. The answer to the Fermi paradox will fundamentally shape humanity's cosmic future. If we're alone, we bear the responsibility of spreading life and intelligence throughout an empty universe. If we're not alone, we must prepare for contact with minds that may be as far beyond us as we are beyond bacteria. But whether alone or not, our survival might depend on becoming something more than purely biological. Life might be the universe's greatest hitchhiker, spreading from world to world on cosmic winds, riding meteorites across the darkness between stars. Panspermia, the theory that life spreads throughout the universe via comets, asteroids, and other celestial bodies, offers a radical explanation for how biology conquers the cosmos. Instead of originating independently on every world, life might have a single common ancestor that traveled between planets, seeding the galaxy with the building blocks of consciousness. We know that rocks regularly travel between planets in our solar system. Meteorite impacts on Mars blast debris into space, some of which eventually falls to Earth as Martian meteorites. Scientists have found over 200 confirmed rocks from Mars in terrestrial collections, proving that natural processes can transport material across millions of miles of space. Think of these meteorites like interplanetary spore capsules, carrying microscopic passengers on journeys lasting millions of years. The vacuum of space provides perfect preservation conditions, no oxygen to cause decay, no water to break down organic compounds, and radiation levels that might actually help preserve biological materials. Some bacteria and other microorganisms show remarkable resistance to the harsh conditions of space. Tardigrades, microscopic animals also called water bears, can survive decades in the vacuum of space, withstanding radiation levels that would kill humans instantly. When rehydrated, they resume normal activity as if nothing happened. Experiments on the International Space Station have exposed various microorganisms to the space environment for extended periods. Many survive the experience, and some even reproduce more rapidly in microgravity conditions. These findings suggest that life could potentially survive interplanetary journeys lasting months or years. But interstellar panspermia presents much greater challenges. The journey between star systems takes millions of years, even for the fastest moving objects. Cosmic radiation, temperature extremes, and the simple passage of time would test the limits of any biological preservation system. Some researchers propose that life spreads not as living organisms, but as complex organic molecules that serve as templates for new life on suitable worlds. These molecular blueprints could survive interstellar journeys while retaining enough information to bootstrap evolution on planets with the right conditions. Directed panspermia suggests that advanced civilizations intentionally spread life throughout the galaxy by launching biological payloads toward promising star systems. These alien gardeners might use self-replicating probes to distribute genetic material, creating a galaxy-wide network of related biospheres. If panspermia is real, it could explain the apparent speed with which life appeared on early Earth. Rather than requiring billions of years to evolve from scratch, terrestrial life might have started with a head start provided by genetic material from older civilizations. The theory also offers hope for finding life elsewhere in our solar system. If Earth life originated from interplanetary exchange, then Mars, Europa, Enceladus, and other worlds might harbor organisms related to terrestrial biology. We might discover that we have cosmic cousins living beneath the ice of Jupiter's moons. DNA analysis of extremophile organisms on Earth sometimes reveals genetic sequences that seem too complex to have evolved in terrestrial environments alone. These biological signatures might be echoes of our cosmic origins, genetic postcards, from civilizations that seeded our world billions of years ago. If humanity ever develops the technology to seed other worlds with life, we would be continuing a process that might be as old as the galaxy itself. We could become cosmic gardeners, spreading the genetic wealth of Earth to sterile worlds throughout the local neighborhood. Our future among the stars might not be about escaping Earth, but about spreading Earth everywhere we go. The choice facing humanity is simple yet profound. Evolve into a cosmic civilization capable of surviving the death of stars, or remain forever trapped on a single world awaiting extinction. Becoming a truly spacefaring species requires more than just building better rockets or developing faster propulsion systems. It demands a fundamental transformation of human consciousness, biology, and social organization. We must evolve from planetary creatures into beings capable of thriving in environments that would instantly kill any Earth-born organism. The transition will happen in stages, each representing a quantum leap in our capabilities and cosmic perspective. First comes mastery of our own solar system, establishing self-sustaining colonies on Mars, mining asteroids for resources, and building rotating habitats in space. This phase could begin within the next century if we maintain our current rate of technological progress. Think of this first phase like learning to walk before we can run. We need to prove that humans can live and reproduce in space environments, develop closed-loop life support systems that work for decades, and create technologies for manufacturing everything we need using space-based resources. The second phase involves reaching nearby star systems using whatever propulsion technology we can develop. Whether through generation ships, fusion rockets, or exotic physics we haven't discovered yet. The first interstellar colonies will mark humanity's transition from a single world species to a multi-system civilization. But the real transformation happens in the third phase, when human settlements become self-sustaining across multiple star systems. At this point, we achieve true cosmic redundancy. No single catastrophe can eliminate our species. We become immune to asteroid impacts, supervolcano eruptions, gamma-ray bursts, and even the death of our home star. This distributed civilization would need to develop new forms of government, economics, and communication adapted to the vast distances between worlds. A message sent from Earth to Proxima Centauri takes 4.25 years to arrive. Building consensus across interstellar distances requires patience and planning on scales no human society has ever achieved. Light-speed communication lag means that interstellar colonies will be effectively independent from day one. They can't call home for help or wait for instructions from Earth. Each colony must be completely self-sufficient, capable of solving any problem with only local resources. Advanced spacefaring civilizations might barely resemble modern humans. Genetic engineering could adapt our bodies to different gravity levels, radiation environments, and atmospheric compositions. Cybernetic enhancements might allow direct interface with spacecraft systems. Digital consciousness could enable exploration of environments too dangerous for biological bodies. The energy requirements for true cosmic civilization dwarf anything we can currently imagine. Building Dyson spheres, accelerating generation ships to significant fractions of light speed, and terraforming entire worlds requires power sources on stellar scales. Mastering fusion, antimatter, or exotic energy sources becomes essential for cosmic-level projects. Perhaps most importantly, becoming spacefaring means accepting responsibility for preserving and spreading life throughout the universe. We might be the only conscious beings in our cosmic neighborhood, making us the custodians of billions of years of evolution. Our expansion could determine whether intelligence survives and flourishes among the stars, or whether consciousness remains a brief flicker in an otherwise lifeless universe. The alternative is sobering. Every species that remains bound to a single world eventually faces extinction. Stars die, planets become uninhabitable, cosmic catastrophes reset the evolutionary clock. Without spaceflight, consciousness itself might be nothing more than a temporary phenomenon in an indifferent cosmos. But if we succeed in spreading beyond Earth, we could become something unprecedented in cosmic history, a species that outlives the stars themselves. Our descendants might witness the formation and destruction of galaxies, guide the evolution of life throughout the cosmos, and possibly even survive the heat death of the universe. The journey from planetary to cosmic civilization represents the next great chapter. In human evolution, we stand at the threshold of this transformation, with the technology to begin serious interstellar exploration within our lifetimes. The question isn't whether we can leave our solar system. The question is whether we have the wisdom and determination to become worthy of the stars, and whether we're willing to transform ourselves into something new to make it happen. So will we ever leave our solar system? The answer is both simpler and more complex than you might think. Physically, yes, we absolutely can. The laws of physics don't forbid interstellar travel. We've already sent probes beyond the heliopause. We've proven that human-made objects can survive in interstellar space. The technology exists in theory to reach other stars within human lifetimes using nuclear pulse propulsion, fusion ramjets, or even antimatter engines. We could build generation ships tomorrow. If we committed the resources, Breakthrough Starshot could launch within 20 years. But the real question isn't about physics or engineering, it's about survival. Will we exist long enough as a species to develop and deploy these technologies? Or will we destroy ourselves first through climate change, nuclear war, artificial intelligence gone wrong, or some other catastrophe we haven't imagined yet? Every year we remain confined to Earth is another year we're vulnerable to extinction from a single event. An asteroid impact, a supervolcano eruption, a nearby supernova. Any of these could end human civilization in hours, erasing billions of years of evolution in a cosmic instant. The Great Filter might be waiting ahead of us. Perhaps every technological civilization reaches a point where they gain the power to destroy themselves before they gain the wisdom to spread among the you. Stars. We might be approaching that precipice right now. Or perhaps we're already past the hardest part. Perhaps the difficult step is developing intelligence at all, and once you have it, reaching the stars is merely a matter of time and determination. In that case, the galaxy might be waiting for us, empty and ready for human expansion. The physics tells us it's possible. Project Orion could work. Breakthrough Starshot could work. Generation ships could work. Even the exotic technologies like Alcubierre drives might work if we discover new physics. The universe hasn't locked us in our solar system, we've locked ourselves in through lack of will and resources. But here's what should keep you awake at night. We're running out of time. Not cosmic time, but civilizational time. Our sun will remain stable for 5 billion years, but human. Civilization might not survive the next 500 years at our current trajectory. Climate change could make Earth uninhabitable within centuries. Nuclear weapons could end civilization in hours. An engineered pandemic could wipe out most of humanity before we even understood what was happening. We've given ourselves the tools to destroy our only home before we've built ourselves a backup. The next few centuries will determine whether humanity remains an evolutionary dead end or becomes something truly cosmic. Will we be another civilization that destroyed itself before leaving its cradle? Or will we be the species that survived long enough to spread consciousness throughout an otherwise empty universe? The choice is ours, and we're making it right now through every decision about resource allocation, technological development, and global cooperation. Every dollar spent on fusion research brings us closer to the stars. Every treaty that prevents nuclear war buys us more time to develop interstellar capability. All we have to do is take the first step off our planetary shore and into the cosmic ocean. The technology exists, the destinations exist. The only question is whether we'll exist long enough to use them. So will we ever leave our solar system? Ask yourself, will you do everything possible to make sure we survive long enough to try? Because that's the only answer that matters. The universe won't come to us. We have to go to it. And we have to start now before it's too late. The stars are waiting. The question is whether we'll be there to meet them.